Week one, right? This article looking at completed schooling as a function of family income just keeps coming back to us, right? We used it to illustrate just a regular regression. We used it to illustrate what a spline regression was all about. We used it to illustrate what dummy variables as independent variables were all about. So that was the first 4 columns. We won't actually do the last 4 columns, but the middle 4 is what we're going to be doing today. So years of completed schooling was a nice, fairly continuous variable. Suppose that your particular interest was in high school completion, right? So whether finished 12 or more years of schooling. And that's a 1-0 variable. Either you did or you didn't. So it ends up being treated differently. And when we did this article, we used a logistic regression model, which is what we'll talk about today. We got this coefficient of 0.23. And we'll talk about what the 0.23 means. But notice first that all the things that you can do with linear regression over here in the first 4 columns, you can do with logistic regression. So you can have a single variable, you can do a spline function, you can take the natural logarithm of income in this case, you can do dummy variables. So it's really just taking a lot of the tools that we've already developed for just a straight up linear regression and applying it to this particular case where the dependent variable is dichotomous. So let me stop sharing here. Oh, by the way, we have a new camera. I hope it's good. I might be a little bit herky-jerky because it's my iPad camera, but at least it's a clearer picture, right? And it doesn't, the focus doesn't come in and out, which I'm sure was driving you crazy. When I looked over the videos, it would drive me crazy too. So let me just comment first of all on a general principle in statistics that variation is a terrible thing to waste. In particular for a dependent variable, right? So we had a nice continuous years of education variable. It wasn't perfectly normally distributed, but it had a range from 8 years up to 18 years. In general, if you have a continuous variable, you should take advantage of the fact that you've got that continuous variable. It's nice to have as much variation as possible because that enables you to distinguish among the independent variables you're trying to explain, or that you're trying to use to explain the dependent variable. So sometimes people have a continuous variable. This happens in medical research a lot. And then they reduce it to a 1-0 variable. It drives me crazy, right? It throws away all this information. But suppose, I mean, sometimes you're just stuck with a dichotomous variable. Sometimes the world dishes out things as either yes or no. And we're going to talk about those situations now. All right. So in the article, we had family income, 15-year family income, just as before, 10, 20, 30,000, 40, 50, all the way out. So that's exactly the same. What's different now, instead of completed education as a continuous variable, we've got a 1-0 whether completed high school. All right, so everybody takes on 2 values, 1 or 2 values in that variable. 1 if they completed high school, 0 if they didn't. So the scale just goes from 0 up to 1. And if you think about the scatter, you know, it's not the typical kind of scatter that we have been used to. Everyone has either a 1 or a 0. So if we think about the 1s out here and the 0s down here, and think about the scatter, we'll have just a bunch of dots along here. And similarly, we'll have a bunch of dots down here. Right, and if we think, as we know from the continuous education variable, that completed schooling and family income are positively correlated, we should have a relatively higher concentration of dots in this portion of the 0 distribution, and a relatively higher proportion of 1s as we go up the family income distribution. All right, so those are the data. What if we ignore the fact we've got a 1-0 variable and just run a linear regression, right? You specify a dependent variable in Stata, and you specify independent variables in Stata. And instead of having a variable that's completed schooling, you put in a whether completed high school, a 1-0, and tell Stata to give you a best fitting regression. Right? That's not an impossible task. It just takes these dots. Not sure what the line's going to be, but something like that, and does the same residual sum of squares minimization that we did when the dependent variable is continuous, right? So all these variables are some distance away from the best fitting regression line. You take that distance and you square it. These dots are closer. You take that distance and square it, right? Add all those up, just as we did before, and find the line, the slope of the line that does as good a job as it possibly can in minimizing those residual sum of squares. And you'll get a slope, right? The equation will be a 1-0 whether finished high school is A plus B1 income plus B2 other controls. Right, looks like a perfectly normal regression. The B1 that you get is around 0.03 and a standard error of about 0.01, as it turns out. So one first question is, how do we interpret this coefficient if it was from a regular regression and not a logistic regression? Well, same as before. What's the slope of this line? It's 0.03. That's all the, you know, when it was years of completed schooling, the slope was 0.14. If it was a spline, the first portion of this spline had a slope of 1.37 or something like that. So nothing out of the ordinary here. And so this 0.03, we've got a 0-1 variable. So this is saying that $1,000 increase, $10,000 increase in family income is moving you 0.03 along the way from a 0 to a 1. All right, so that's That's one way to think about it. But it's easier and more natural to think about a 1-0 variable as a 0 to 100 probability. So you want to convert from a fraction to a probability. And that's pretty easy to do. You know, suppose someone said, well, I've got a group of 500 people who are almost exactly like you. And suppose you had not suppose you had not attained the age where you could complete high school. So you're 10 years old. And someone says, well, when I look at a bunch of 10-year-olds, when I looked at a bunch of 10-year-olds several years ago, they were very much like you, and 50% of them finished high school. All right. I'd say, well, my own probability of graduating from high school, if those people are very much like me, is 50%. Right? It's a very natural thing. So 0.5 translates to 50% probability. If I said, well, 75% or 3/4 of your similar peers finished high school, I'd think, well, maybe I've got a 75% probability of finishing high school if that's the case. You know, 0.25, 25%. Another way of thinking about probability is percent chance. And it's a very natural way to think about things. So you lose nothing and you gain a lot when you're thinking about a dependent variable. To think about that 0-1 variable as a 0-100 probability. All right. So now this is the same as probability of finishing high school is A plus so now we're going from 0.03 to 3%. It's really B1 times 100 income plus other stuff. So 0.03 becomes a 3% and standard error of 1%. So that makes things very easy. We see a 0.03 and we think, well, what that means is that every additional $10,000 of income is associated with a 3% increase in a chance of graduating high school. Everybody follow that? Any questions?
Greg?
Yeah.
Do you mean 3 percentage point? Not, or 3?
Yeah, that was my next point.
Okay.
Yeah, so there's this distinction between percent versus percentage point. A percent increase, let's say, versus percentage point increase. Sometimes abbreviated PPT. So what we're really talking about here, Paul's right, is a percentage point increase. So if we, let's say I'm in a group where half of the people graduate high school, my baseline chance is 50%. What this regression would tell me, if it's causal, is that $10,000 more family income for 15 years would increase that chance from 50% to 53%, right? So you're going from 50% up by 3 percentage points to 53%, right? And what's confusing is if we just think about a percent increase, you know, how much larger is 3 above 50? That's a 6% increase, right? That percent increase varies with the base. So, you know, sometimes a percent increase interpretation for things is clear for people. But if you're talking about these probabilities, you're almost always talking about percentage point increases. So that's good to note. People make this mistake all the time. And now you can correct them when they do. But what comes out of a regression is going to be a number like 0.03. And that, in this case, is a 3 percentage point increase.
Greg, I have a question.
Sure.
In what case would it not be a percentage point increase?
It's always going to be a percentage point increase. But to interpret that as a percent increase that's going to vary all over the place, right? A 3 percentage point increase, it's 3 percentage point increase up here, 3 percentage point increase down here. It's a linear function, right? So if you think about it in terms of just percent increase, as I say, if you're starting at 50%, starting at 50 and go up by 3 points, that's a 6% increase, right? If you're starting at 1% and go up to 4%, you're quadrupling the
I see.
right?
Yeah.
So in one case, it depends on the base, and the other case, it's base free. And the percentage point interpretation is base free. And that's exactly what the slope of a linear regression is. It's base free. It's a constant slope. It's 0.03 up here. It's 0.03 up here. Down here, it's 0.03 down here. So it's 0.03, 3 percentage point increase, regardless of where you are in the curve, right? But in contrast, the percent increase, if you always have a 0.03, is changing constantly as you go up and down because the base is changing.
That makes sense. Thank you. I was always confused about that in undergrad. Thank you.
Well, many people are confused in graduate school and beyond. So it's one of those things that it's good to keep straight. So what's wrong with this picture, right? We've got regression. We've applied, it's a best fitting line. It's giving us a slope. We've got a nice interpretation of the slope. So this, by the way, is called a linear probability model. LPM. And it's used a lot, almost exclusively by economists. So, you know, I mean, economists are wrong about a lot of things, but I don't think they're wrong in using linear probability models a lot. It's good for, I mean, what's nice about a linear probability model is that it gives you such transparent results. You see a coefficient, and it tells you the percentage point increase when you multiply it by 100. And that percentage point increase is assumed to be constant. What is wrong with this, once you get statisticians involved, it's just no fun anymore. And that's true here. Two things offend statisticians about a linear probability model. Problems with linear probability model. One, you get predictions below 0 and above 1. Not in all cases, but here you've got this portion of the regression line is sitting up above 1. So if you're trying to predict someone's probability of graduating high school with a high income, your prediction is a number that's greater than 1. Or down here, I drew it through the origin, but that doesn't have to be the case. You could easily have predictions below 0, which doesn't make any sense, right? You can't have a probability of graduating less than 0 or a probability of graduating greater than 1. So that's one source of offense. A second source is non-constant variance along the x-axis, along the x variable distribution. All right, if you want to impress your friends, one of your assignments for next week is to drop the word heteroscedasticity into a conversation. All right, I want, maybe that'll be my one assignment, is to describe how you slipped heteroscedasticity into a conversation with a friend who's not in this class, by the way. So it's heteroscedasticity. And what that means is it's non-constant variance. So the classic regression model has various assumptions associated with it. And one of it is that the variance of the x's around the regression line is similar all the way up and down the value of x. And the nice properties of OLS regression hold, assuming that there's constant variance, assuming there's a normally distributed dependent variable, right? All these assumptions. And it's pretty clear that this heteroscedasticity, if you think about the variance you should go along here, is not constant. It turns out OLS is pretty robust. There have been a lot of simulation studies of this, pretty robust to departures from normality on the distribution of the dependent variable. Maybe I should say that, distribution of dependent variable. And I get to say it again, heteroscedasticity. So in fact, these aren't big problems. But again, it offends the statistician's conscience. So they come up with a different approach. And that approach is logistic regression. So to think about logistic regression, let's erase some of these things. Get back to our scatter of points. That's what we're stuck with. So what we need is some function that we can apply to these data that that won't produce predictions beyond the 0-1 range, right? And it turns out there are a number that you can come up with, but there's one that has this nice S shape. It's a logit function. Another one is a probit function. People use logit and probit pretty interchangeably. Economists tend to use probits, and education people tend to use logistic regression. They make different assumptions about the distribution of the error term in the equation, but they give you results that are very, very similar in terms of what variables matter and what variables don't. But these logistic regression functions and probit functions, let's just stick to logit for now, have this S shape. They can't go below 0. The function is set up so it can't go below 0 or above 1. But what's annoying about it is the coefficients come out in ways that are much less interpretable than the coefficient to the linear probability model, right? And you can see right away why that's the case. In a linear probability model, we had this 1-0 variable. We were regressing on income and controls. We got a number for the slope, right? There was a slope. It was 0.03 everywhere. And that slope, that 0.03, had that probability interpretation, which is the way people think about these things. If we think about what a logistic regression implies about the probability of completing high school, in other words, what the slope of this function is, the slope is constantly changing, right? If we've got low levels of income, we've got a slope that might be, let's say, 0.02. If we've got 35,000, now the slope, whoops. Trying to draw a tangent to this curve. Now the slope might be 0.07, and up at the top here, the slope might be bit down to 0.03. So those 0.02, 0.07, and 0.03, those have the probability change, percentage point change interpretation with the linear regression. But what's tricky is that it's constantly changing as you go up the curve, right? So your answer, if you say, just tell me how to think about this in terms of percentage point changes, people are going to say, well, where do you want to be on the curve to get a figure for the percentage point change in completing high school that I would expect from that baseline? So what we'll do is talk about logistic regression. We'll talk about the coefficients from a logistic regression. And then at the very end, we'll talk about how to convert logistic regression coefficients or probit regression coefficients back into probability interpretations, right? So that you can, when you're explaining things to the reader, not talk about an odds ratio or not talk about the log of the odds ratio, which is hard for anyone to think about. And instead you can convert it into probabilities. But it's got to be a probability evaluated somewhere, and we'll mix that in. So I kept up our chart here. And just to remind you, we're talking about P as a probability of some event occurring. A linear probability model can be thought of as that probability as a function, linear function of family income. Actually, this isn't right. If we were to run a linear probability model, according to my calculations with these data, we would get a coefficient on family income scaled in tens of thousands of dollars of 0.03, which, as we said, means that additional $10,000 of family income is associated with a 3 percentage point increase in the probability of graduating high school. All right, and we were marveling at how clear that was to everybody. Logit regression transforms P, which it has to do if it's going to be nonlinear, right? It's got to be some sort of transformation. And it's a pretty ugly transformation. It's the natural logarithm of the odds of P occurring. So we've got ln P over 1 minus P. This is just the natural logarithm function. And P over 1 minus P are the odds of event occurring.
Greg, I have a question.
Sure.
I don't think I understand the difference between what odds are and what the difference is between odds and probability. I thought they were the same, but apparently they're not.
They are not, because odds are the probability divided by 1 minus the probability, right? Simply stated, but odds are P over 1 minus P. So let's say P equals 50%. What are the odds? 0.5 over 1 minus 0.5. Which is 1, which people say are even odds, right? So if it's an even odd, if it's an odds ratio of 1, that translates directly into a probability of 50%. So they're not at all the same. Yeah, go ahead.
But aren't they both conceptually speaking to the same thing about like the chance of something happening?
Not the chance, right? Chance is a probability idea, right? Percent chance. And so that's all about P. We're taking P and we're transforming it by dividing by 1 minus P, right? So we're talking about a change in the odds of something happening rather than a change in the percent chance of something happening, right? They're both sort of talking about the same thing because they're both a function of P. One is P directly and the other is this transformation of P. Let me keep going here and you can see if it makes sense. Suppose you had a 2/3 chance of something occurring. Well, the odds would be 0.67 over 0.33, right? 0.67 over 1 minus 0.67, which is 2, right? 2 to 1 odds. If P is 33%, we've got 0.33 over 0.67, which is 1/2. So it's the odds are 1 to 2. So in a way, you're talking about the same thing, but not really talking about the same thing. And you know, a number of people interpreted this 0.23 in terms of percent change, right? And high school dropout is a function of family income. And that's a very natural interpretation, but it's the wrong interpretation. What you literally are getting is the log of the odds changing by 0.23. All right, so, you know, who knows? I haven't met anyone who can immediately come up with an intuitive interpretation for a log odds. You know, some people think in terms of odds. Medical research is all about odds ratios and risk ratios, which are similar. You know, bookies talk about odds. So, you know, they're pretty good at thinking in terms of odds. But, you know, normal people like the rest of us, or at least like you, think in terms of probabilities. So we're kind of at a disadvantage here, but we've got to cope with it, right? Because this has been pronounced as the way to think about the proper way to do a regression when you've got a 1-0 dependent variable. So the model is ln p over 1 minus p equals a plus b1 income. Now it's the case, if you think back to algebra, that e to the log x equals x, right? E and the log function are inverses of one another. So let's take e to the ln p over 1 minus p equals e to the a plus b1 income. But e to the log of something is just that thing, which is the odds ratio. So that odds ratio is a function of e to the a plus b1 income. Still not getting clearer, is it? But you can see now, suppose you did think in terms of odds. How do you translate this b1 into a change in the odds? Well, if you think about it, we're going from a baseline set of odds to a new odds incrementing by b1. And if we're making a 1 unit change in income, that's what b1 is showing, what the effect of a 1 unit change in income is. We just have the change in the odds is e to the b1, right? We're saying a change in p over 1 minus p as a result of changing income by 1 unit is just going to be b1. So we're left with e to the b1, and that ends up being the change in the log odds. So that's why in the article that 0.23 transformed into a 26% increase in the odds of high school graduation. And we got that by taking e to the 0.23. And if you pull out your calculator and do that, you get 1.259 So let's clear off a little board here. If B1 equals 0, then e to the B1 equals e to the 0, and anything to the 0 power is just 1. All right, so if there was no effect of income on the odds of graduating high school, then we'd have an odds change, or an odds ratio of 1.0. So 1.0 is the baseline for odds ratios changing. So we went from 1 to 1.26. So going from a 0.26, a 1.26 change in odds is a 26% increase in the odds. So it's all relative to 1. If it's a positive coefficient, if B1 is positive, then we're going to get something bigger than 1. If let's say if B1 turned out to be minus 0.15, then e to the minus 0.15 equals 0.86. So relative to 1, that's a 14% decrease in the odds of high school graduation. All right, I went over that quickly. What questions do you have?
Greg, I have a quick
Yeah.
question.
Sure.
Could we also represent the equation of saying it's like e to the B1 minus 1 times 100? That way we could turn it into a percentage?
No.
Okay.
I mean, you're still dealing with odds, right?
Mm-hmm.
So you're getting a 0.26 difference between 1.26 and 1, but you can't interpret that 0.26 as a change in the probability because it's a percent change in the odds,
Mm.
right?
Okay.
So,
yeah, I see what you're saying.
you know, I told you this is going to be annoying, and it is. But this e to the B1 is the way when you see, the regression table, the logistic regression table in that article had a coefficient of 0.23, right? That was the one that I asked you to interpret. And, some of you wanted to say a 0.23 increase in the chance of high school graduation. That's not right because it's an odds ratio increase, but it's not even a 0.23 increase in the odds ratio because it's an e to the 0.23 increase, minus 1 in the odds ratio. So a number of you got 26%. I'm not sure if you cranked this through or whether you looked in the article to see what I said the increase was. But now you know. Right? So, you know, if someone insists on, you can present logistic regression in several ways, results. You can do what I did, 0.23. And then it's log odds. You can present coefficients and standard errors that are exponentiated, right? You can take e to the 0.23, and Stata will do this, and e to the 0.07. Actually, e to the 0.07 is quite right, but you get e to the 0.23 for the coefficient. So you'd get, in a table like that, you'd get 1.26 as an odds ratio. It's still not ideal because it's not a percentage interpretation, right? Which everybody wants, because that's what the most natural way to think about it is. So that's why there is in Stata a command called margins. And what margins does, margins, among other things, converts log odds ratios into probability changes. At either average values of all your x variables or any other place along the logistic regression line that you choose, along the logit that you specify. Okay, why is that so complicated? We're trying to get a probability interpretation, percentage point change associated with, in this case, an additional $10,000 of income. And there's not one answer, right? We keep going back to the curve. There's a percentage point change that's pretty low down here. There's a percentage point change that's pretty high in the middle. There's a percentage point change that's much lower at the top. So if you want to get a percentage point interpretation, you've got to tell margins where to do the evaluation. Okay, and what people usually do is say, give me that probability interpretation from this logistic regression at the mean of all the independent variables. Right, so that's a reasonable place to do an evaluation, wherever the mean is. What's the corresponding change in the probability at that point? If you want to know down here what it is, you can plug in a value and it will tell you what the probability is. If you want to go up here, you can do the same thing.
I have a question.
Sure.
Going back to the interpretation in the middle of the board where it says 14, well, let's do the top one. 1.26 change in odds is a 26% increase in the odds. What is it a 26% increase in the odds of? Is it like a 1 unit change in income?
Yeah, all these things are a 1 unit change in the independent variable in your regression, right? So in our case, income was scaled in tens of thousands of dollars. So we had a 1 unit change being an additional $10,000 of income for 15 years of childhood. And that was associated with a 26% increase in the odds ratio of graduating high school. And as it turns out, that's at the average, at the mean, that's about 3 percentage points. That's where I got that 0.03 from.
Yeah, sorry, I have a question.
Sure.
So is it the same if you would have like calculated probability from like a logarithmic function, like a sigmoid or something? It would have given like the same result as this, right?
There are a number of these functions, as I say, the logit and probit are the most popular, that essentially fit a similar S shape. So, I would bet, it's certainly the case with logit and probit. You can run margins on probit also. You get different coefficients because they mean different things, but you do margins, translate into probabilities, and you get exactly the same result pretty much that you get from a logistic regression evaluated at a particular point along the X distribution.
Yeah. So my question was like, we are just like trying to give the C plus D1 family income into like a S-shaped function, right? This is like our input and S-shaped function.
Yeah, you want it to be a function.
Which gives us the probability, right?
Well, and you want the function not to offend statisticians. So it can't go below 0, can't go above 1, right? And then you want to, whatever results you get from that function, you want to be able to translate them into a probability change, because that's the way people think about it. And, indeed, were I to do this research today, I would present, I wouldn't run a linear probability model, I'd run a logistic regression, but I'd present all the coefficients and standard errors using margins at the mean of all the X variables in the sample, right? Just because I want readers to understand right away when they look at a coefficient what it means, right? And if you use margins, you're translating that logit function into probability changes, and that's the easiest thing for people to understand.
Yeah, thank you.
Sure.
Can I ask another? Oh, go ahead,
Sure.
Vanessa.
Okay, I was going to ask, so you're saying that the margins is at the mean of all independent variables. So I guess I'm just a little bit confused as to why it's all independent variables when it should the estimate is based on like the income variable.
So with margins, you can tell it anything you want in terms of where to evaluate the logistic function that you've estimated in when converting it to a probability, right? So the default, which most people use, we've got family income, and you might want to use mean family income. You might want to use $20,000 of family income, right? That might be more relevant for your research, because you really don't care about middle and high income families. You're just interested in low income families. I should say there's nothing about, as with a linear probability model, there's nothing about the shape that can adapt to a kind of a it's non-linear, but with completed years of schooling, it ended up being non-linear with income, right? That spline, it was a pretty responsive education at low levels of income, and then it flattened out a lot, right? This could be doing the same thing. And indeed, if you look at, let me bring up the article again. So here's the 0.23. But if we allow for a spline, right over here, remember we allowed when it was just years of schooling, it looked like every additional $10,000 was only associated with a 0.14, about a seventh of a year of schooling. When we allowed for that schooling to be much more responsive to income at low income, we found it was 10 times more responsive, the 1.30 as opposed to the 0.14. So in this second model, we allow for the odds, log odds of completing high school to be much more responsive at low income levels to income increases than high income levels. You know, this could have been 0.23 and 0, which would have indicated that things were exactly the same, 0.23 all the way up and down. This could have been 0.14 and 0, which would indicate, you know, just an overall linear form. Fits pretty well, but that's not what the data said. The data said big response at low income, smaller response at higher income. And in this high school completion spline function, you get exactly the same thing. It's not a 0.23, it's a 1.97 per $10,000. I don't know what e to the, wait a minute. I've got my calculator. So 1.97 e to the x, 7.17. So we have a 7-fold increase. If we're looking at this 1.97, a 7-fold increase, not a 26% increase, a 700% increase in the odds of graduating high school with an additional $10,000 at low income. And then once you get above 20,000, it's this difference, right? Which we're kind of back to, well, now we're down to 0.13. So it's 1.97 below 20,000 and only 0.13 above it. And that kind of averages out to this 0.23. So there's, you know, if you're evaluating this logistic function down here at a low income level, the logit imposes, it's linear in the log odds of graduating high school. It's linear in that log odds. So it's just taking the coefficient and figuring out, plugging in different values of income, what that linear function looks like. But it's not linear, right? If you look at the table, that spline was a very significant variable. So, you know, God knows what this function looks like as a function of family income if you allow for a spline. You know, obviously up to here there's one function, and then up here there's some other function. I've never tried that to actually graph it out. But the point is that if you're interested in what the probability change is at different points along this distribution, you've got to realize that you impose this functional form that's linear in the log odds in the same way that family income, before we did the spline, we got that 0.14, that was imposing a linear in the probability form. So this can be very restrictive, and just because it's nonlinear doesn't mean it's more responsive at any particular point in the distribution. If you want it to be differentially responsive, you need to set up your X variables to test for that. And that's what the spline function does. That's what the dummy variables do. They allow for that difference. Other questions?
I have one about interpretation again. In the Damaris article,
Right.
the terminology as large as. So when he was talking about being happy and whether or not you're widowed, he says as large as for something. Would that be interpretation in terms of the odds ratio? So can I say, for example, on the board it says is a 26% increase in the odds ratio. Can I also say is a 0.2 is 0.26 times as large. Would that be the same interpretation?
No. That's you're getting back to probability.
Oh, that's still probability?
Well, what's 26 point? Say it again, what you said. It sounded like a probability statement.
I wrote down exactly what he wrote. He said the odds of being unhappy are 3.5 times as large for widowed people as they are for married people.
Right. So here it's 26%. Well, it's 1.26 as large, as opposed to 3 times as large. So yeah, his statement is right, but it's completely consistent with what we were talking about.
Okay, so we can represent it as either 1.26 or 26% increase?
Well, it's 1.26 as large, right? And that's a 26% increase. Those are the same thing.
Is one
Doesn't it?
preferable over the other?
You know, I think most people respond to 26% increase in the odds. You have to make sure you say odds because they're going to think probability. But, you know, as I say, I wouldn't even bother with this. I'd get a probability interpretation and say that it's, you know, you're going to get something like a 3 percentage point increase, probably. And, you know, that's the easiest way to think about it.
So if you had a scenario where it was 1.99%, there's a 1.99% change in odds, that would be a 99% increase. But if you had a 2.01 change in odds, would that be a 101% increase?
In effect, I mean, it would be doubling the odds ratio, right?
Yeah, it would be double plus 0.01.
Yeah, right. So, you know, that's right. That's a that's kind of a quirk of how we talk about things. But those, you know, doubling the odds means going from 1 to 2, right? So again, we're talking about the same thing.
Okay, thank you.
Okay, any final questions? As I look to the clock, isn't it nice we're so aligned in terms of our desires for the rest of the afternoon? But here, so you get an extra amount of time. Pull up that exam right away, and you know, give it a half-hour look, and you know, get an orientation toward the kind of questions there are, and start to think, you know, what your answers would be. Start to think what your questions are, and if you've got study groups, you know, get together with your study group, because you ought to be able to answer all those questions except for the sibling question.